Hello, everybody. My birthday's coming up in a month, and I know that you're all thinking about what you'd like to get me, and I have the answer right now. I would like you to make me a paperweight, and I have a specific kind of paperweight in mind. First thing is that see this shape right here, this circle. I would like the base of the paperweight to be about this size. So this is not a paperweight. This is a candle, but you can see the candle has a circle for the bottom. I like it to look something like that. However, here's kind of my vibe. This is the style that I'm going for. And if you cut a cross section through this candle, like cut it right there, each one of the cross sections would be a rectangle. And I'm going to say, rather than a rectangle, I would like each one of the cross sections to be a square. So let's see what this is going to look like. I'm going to try to draw this in 3 dimensions. Doing my best here. So here's X, here's Y, here's the circular base. And what's going to happen is that popping out of the paper, right in the middle here, this would be one side of the square, and the other side of the square would look something like this. So there's the cross section. But as we move closer to the edge of the circle, like if we moved up here, you can see that the side length of the square is smaller, which means it's not going to pop quite so far out of the paper. And if we move up here, you're going to get like a really small cross section like that. So it's going to end up having this sort of flared piece like so. Pretty cool, huh? I'm so excited that you're going to make this for me. So let's talk about how you figure out the amount of material that you're going to use or the volume that this is going to take up. The first thing that you need to do is you need to look at your cross sections. So the cross section is a square. And what you want to do, step 1, is to write a formula for the cross section. So the area of a square, sometimes I'll ask students, what's the area of a square? And they'll say, well, it's its base multiplied by its height. Well, that's true, but we really don't want to have 2 variables here. So think about, can you simplify it a little bit? And the answer is we can. We can say whatever the side length is down here, I'll call it S. We're going to have the same side length up here. They're equal to each other. So a better formula would be S times S, or side length squared. Okay. So that's step 1. Step 2 is to think about where your volume would come from. In this case, the volume of our paperweight is going to be equal to what we get when we add up all the little squarey cross sections. So it's going to be the sum of the square cross sections and since we have an infinite number of these little cross sections, we find that sum by taking the integral. And this would be the integral of the squares. So in here, I'm going to say that each one of these cross sections has 2 things going on. First, it has the side length squared. So this formula right here, I'm bringing it down here. Side squared. Multiplied by, each one of these is going to have a little bit of thickness on it. Now, if we come back to the actual problem, it says that the cross sections are perpendicular to the x-axis. So if I were to draw them on the flat image right here, a cross section would look like so. Or in other words, the side that you see down here is this side right here. And the thickness would be this little piece. Just like we've been practicing, we can see that that's a little change in x, a dx. So I'm going to put a dx in right here. Okay. Now, next thing is we need to figure out what goes in this space and what our bounds are. So this is where we need to bring in the equation of the base, which is a circle. That equation is this. Now, you guys probably remember that when you have a circle equation that goes x squared plus y squared equals something squared, this is the square of the radius. So our radius is going to be equal to 2, meaning that we're starting here at x is -2 and ending here at x is +2. So this will go from -2 to 2. And then if we want to find what goes in here, this is the side length. Of the square. Why is it the side length of the square? Well, we defined this right here as the side length of a square. So this side length is the difference between the y value here and the y value here. So I'm going to write that as y1, take away y2. And this one's kind of a weird one. If you want to figure out y1 and y2, you have to solve this equation. And I'm actually going to do this on a separate sheet of paper because I just don't have a whole lot of space here. Solving this equation would go like so. You're going to subtract the x squared from both sides so that you have y squared is equal to 4 minus x squared. And then you're going to root both sides. And remember that when you root, you get two answers. You get a positive and you get a negative. So these two answers, the positive and the negative, they are y1, the positive, and y2, the negative. What that means is that our side length is going to end up being y1 is the square root of 4 minus x squared, minus y2 is negative square root of 4 minus x squared. Okay. So that's what I'm going to plug in. A little more algebra for you. If you have the square root of 4 minus x squared minus negative 4 minus x squared, obviously those are going to become positives, and since we have two of them, it is equal to 2. So that right there is what I'm going to put in for the side length. Okay, let's actually work this one out using the fundamental theorem. To do that, I think it would be helpful to simplify a little bit. So one thing I'm going to simplify is I'm going to shower this power down. 2 squared is going to give us 4. So we've got a 4. I'm actually going to pull that out of the integral because it's not going to affect anything. And then the square root squared is going to cancel. We get 4 minus x squared dx. The other thing that I'm going to do, because I'm lazy, is I'm going to note that this side and this side are mirror images of each other. This is an even function. So one thing we could do is just find the region from 0 to 2 and then double it. So if I change this to a 0 and then I double right here, we're in good shape. All right, here we go. Now 2 times 4 is 8 times antiderivative would be 4x minus antiderivative would be 1/3 x cubed. Evaluate this from 2 to 0. Oh, having the 0 there is great because you can see that when we plug the 0 in, nothing's going to happen, right? So really all we have to do is plug in the 2. 8 times 4 times 2 minus 1/3 of 2 cubed is equal to 8 times 8 minus 8/3. So that's going to be 2/3 of 8 times 8 is 128 over 3. Let's say it's in cubic inches. So that's how much material you're going to need to make the paperweight. Notice what's missing here is that we do not have a pi. Let's try another example. Flip to the next page. I'm going to read this one aloud as you read it to yourself. It says, let R be the region bounded by y equals 3x and y equals x cubed or squared in the first quadrant. Find the volume of the solid with R as its base that has cross sections perpendicular to the x-axis, which are right isosceles triangles. So the cross sections are perpendicular to the x-axis. That means that the cross sections are going to go like this. And then I'm going to attempt to draw this for you. Here's x, here's y. The region that we're looking at is sort of like boom, and boom. And what we would see if this was popping out of the paper is that where it's wide, you get, there's the base of the isosceles triangle. There's the height of the isosceles triangle. You get that. And then over here where that base is not so big, the height of the triangle will be not so big. And so you're going to get little regions that look kind of like that popping up all through this range. Cool. All right. When we're all done, you'll get kind of shape like that. All right. So let's follow the same steps we did last time. Step 1, I need the area of an isosceles triangle. And you don't want to say it's 1/2 base times height. The reason you don't want to say that is that's 2 variables, you want 1. I am going to call this right here a side of the triangle. Specifically, it's this side. Because it is isosceles, you know that this side is the same. So if this is S, this would also be S, meaning that we would get 1/2 times S, or 1/2 of the side length squared. Okay, so that's step 1. Step 2 is to write your volume equation. To find the volume, we are going to sum the 1/2 times the side length squared. So I took this formula and I plugged it in right here. Each one of them has just a little bit of a thickness on it. And you can see that because we've got vertical strips, that thickness is going to be a dx. All right, now 2 things we need to find. We need to figure out what is the side length, and then we need to figure out what are the boundaries. Let's start with the boundaries. Our 2 functions are y equals 3x and x squared. So we need to figure out where they intersect. We can see that they intersect here at 0. The other place that I can just see that they will intersect is when x is 3 and y is 9. If you plug a 3 in here, you get 9. If you plug a 3 in here, you get 9. So we will range from x is 0 to x is 3. And the side lengths will be y1 minus y2, which is 3x minus x squared. Now on this one can be done by hand, but it is an absolute horror show, let me tell you. So instead, let's just grab our calculator and we're going to select finint and input 0, 3.5 times 3x minus x squared dx. You'll notice once again, no pi in our equation. 4.05 units cubed is our answer. All right, I'm going to be quiet for a minute. I would like you to attempt the next problem, which says redo number 7, but this time reorient it so that the triangles are perpendicular to the y-axis. And I want you to figure out, does this change the volume? Let's check our work. First, I attempted to draw a picture so you can see how it's oriented a little bit differently. One thing that we know is that if the cross sections are perpendicular to the y-axis, then your side is going to go in this direction. And if the side is going in this direction, we know right away, zoom out a little bit, that this is going to be a dy problem. Everything else will be the same thus far. Now, because this is a dy problem, we need the line and the curve to be in terms of y, and our side length is going to be the difference between the x value that is further to the right and the x value that is further to the left. The one further to the right is the curve. The one further to the left is the line. So our equation for the side length is going to be this. It will be the square root of y minus y over 3 squared. The other thing that's going to be different is, since we are stacking them up this way, our lower bound will still be 0. But since this point where they intersect is 3, 9, the upper bound will be 9. You put this in your calculator. I already did it right here. Notice when you put it in the calculator, you still got to use x's. And I came up with a different volume than we got on number 7, which is 1.35 units cubed. So the answer to the question is yes, depending on your orientation, right, horizontal or vertical, you're going to get a different volume. Okay, moving along, let's try one more. Take a look at example number 9. We're working with the region that is enclosed between y equals e to the negative x squared, which those of you that know stats, this will be very familiar to you. This is the normal curve. And then y is equal to 0.5, which goes like this. And the region that you're going to be working with is this region bounded between them. Okay, so it's now time to stop the video, and I want you to attempt to answer questions B and C. All right, and here we go. How did we do? I'm taking a look at B. It says that the cross sections are squares, and the formula for that is side squared. I graphed the data and found that the points of intersection are here and here. So the lower bound should look like this. The upper bound should look like this. The side length is the difference between the curve minus the horizontal line. So inside the equation, we should have e to the negative x squared minus 0.5. If you got that, you are good to go. It just says to write the expression, so you do not need to actually calculate the volume of the region. Second one's a little trickier. Let's talk about this one a little more. It says, what if the cross sections are semicircles? So you would get like semicircle, semicircle, semicircle. Lots of little semicircles here. So I wrote the formula for a semicircle. Now there's a problem with this formula in that it's in terms of a radius. And if you look at the segments that we're getting here, that base piece right here, the piece that corresponds to this side length, that's actually the diameter. So what we need to do is take this equation and change it to 1/2 pi times the radius would be the diameter divided by 2. And if we simplify that down, you're going to square this too, see, because it's inside the parentheses. So this is really d squared over 4. The 4 multiplies the 2. We end up with pi over 2 times 4 is 8d squared. So the formula I'm going to put in here is going to be pi over 8 diameter squared dx. The lower and upper bounds haven't changed. The side length, which is the diameter, hasn't changed. So the only difference between your answer to B and your answer to C is right here. It requires the inclusion of a pi over 8. Ta-da! And now you know how to find the volumes when you have the base of a solid. The end.